Greetings, stargazers, and welcome to our next lecture in section 17. This will be our discussion on the high mass stars and their lifespans. So this breaks down. We're going to have three parts of this. We're going to talk about what is the primary source of energy production in the high mass stars. And then we're going to move on to talk about variable stars. These are going to be very important for us in our later sections. These are going to help us get distance measurements in the cosmos. And after we finish talking about the variable stars, we'll move on to discuss the end of the high mass stars, the big, massive supernovas, and all the animations I know you want to see. So as usual, let's go ahead and have our reading quiz, and we'll ask, what is the heaviest element that nuclear fusion produces? I picked a few of these here. Argon, iron, gold, or organosin, OG. This is the heaviest known element. So pause it here, give it a second, and then come back. If you're doing your reading, you'll notice that the periodic table, in terms of nuclear fusion in a star, stops at hydrogen. So, big question. Where does all of this get made? If periodic table only deals with this region, where do all the heavier elements, any element heavier than iron, come from? So in this video, we'll show why fusion stops at iron and discuss where those heavy elements come from. Now let's just dive right into part one of this video, of this section, the energy production and the high mass stars. And this is a schematic representation of it. And it's called the CNO cycle. All right. Bit more elaborate, fanciful picture of this as it goes through every little step. So we'll go through these steps together in a bit. Emphasis. Temperature and pressure are higher than low mass stars. Low mass stars, you've got that core of hydrogen and a bit of helium present. You go to the high mass stars, yes, that's there, but there's also a steady source of carbon also present. All right. The source of that carbon, right, the source of the carbon that's in the core of the stars is basically a previous star generation. A previous star, it fused a bunch of material making tons of carbon, and that star eventually reached the end of its life, ejected its fused material out there, and that material later condensed down into the next generation star. So in these high mass stars, we tend to notice that there's a lot of carbon around, and that carbon's used in this CNO cycle. Right? All these pictures that you've seen in these last three slides are all representations of the exact same process. So let's go through this together. Right? Take your carbon atom, and we're going to send it through the CNO cycle. And hopefully you're starting to see why we call it a cycle. Our carbon will be hit by a hydrogen, a proton. Right? Energy comes out. Photon comes out, you get your energy, and that carbon is now turned into nitrogen. Nitrogen, specifically 13, an isotope. What will eventually happen is that this will decay. What will be ejected out is a positron and a neutrino. Remember neutrinos when we talked about the sun. These tend to just fly rapidly straight out of the star. The neutrinos are not very interactive materials. That positron, hey, that's a source of energy. Think back to our discussion on the sun's fusion energies, the proton-proton chain. A positron will hit with an electron. There'll be matter-antimatter reaction. They annihilate. Boom. This guy will eventually turn into two photons, and that's energy to fuel the star. When this nitrogen does spit out that positron neutrino, it's back to carbon. And oh, look, carbon, it can be hit with hydrogen, photon out, back to nitrogen, only this time, notice the difference. Here we started off with C12. Now we've got ourselves C13. These two guys are both chemically carbon, 6 protons, but their number of neutrons is different. So this carbon, this C13, hits a proton, photon out, and we now have got nitrogen 14. Count the nucleons, 13 to 14. So we have this nitrogen 14. This thing's relatively stable. This thing's going to stick around for a long time. So this guy will also eventually get hit by a proton. Proton hits the nitrogen-14 photon. Delicious energy to power the star. And that nitrogen-14 has turned into an oxygen-15. And just like the nitrogen-13 when it ejected out material, so is this oxygen-15. It'll spit out another neutrino that flies straight out of the star, and another positron that turns into more energy to fuel the star. We're left with this nitrogen-15. This nitrogen-15 is another isotope of nitrogen. What will eventually happen to this thing is that finally the last hydrogen will collide with this isotope of nitrogen. A helium atom gets spit out, and we're back to where we started, carbon-12. So our input is carbon-12, and our final output will be carbon-12. So this is one of the primary energy sources in the high mass stars. Carbon is basically facilitating a bunch of individual reactions, releasing tons of energy. Anytime a photon comes out, or a positron that will eventually annihilate with an electron, that's energy being released. So the presence of carbon allows it to go through this cycle, being converted into other isotopes, other atoms, and then return back to itself to C12. So another way of saying this is that carbon acts as a catalyst for hydrogen burning. Give yourself carbon plus 4 protons and 2 electrons. You're going to get out eventually carbon, helium, 2 neutrinos, and all in total 7 photons. Neutrinos fly straight out. The photons, that's energy that powers the star, allows fusion processes to go. So already we're starting to see how the high mass stars are differing from the low mass stars. The low mass stars just don't have a prevalent amount of carbon in them to facilitate this chain. But with the carbon present, carbon mixed with a bunch of hydrogen, you actually get to accelerate the rate of energy consumption. These high mass stars, like I've claimed multiple times before, they are consuming energy at a much faster rate. Because they're more massive, they have more things to facilitate or, in other terms, catalyze these reactions. Right? Another difference between our low and high mass stars is that the high mass stars, their cores are going to be convective. Right? What do I mean by convective? I mean that heat can transfer by just the movement of heated material. I've got a hot object here and it bubbles over here, and so that heat has transferred. You might recall a plot similar to this on the low mass star discussion. We said, look at the radius of the star versus the percent of mass. Now, just like we had between the high mass stars and low mass stars, initially, at the star's birth, it's going to be some decent percentage of helium and mostly hydrogen. But here's where the change happens. In the low mass stars, our curves over time as the low mass stars age, we got curves that looked kind of like this. Looked kind of like a Gaussian distribution, if you want a name for it. But here, because of the convective nature of the core, there's just this straight line of increasing, right? Those hydrogens are mixing with the helium fusion products, and it's increasing the amount of hydrogen that's available for fusion. Energy is getting produced, and because of the convective nature of the core, more hydrogen is allowed to be burned. Hey, there's more fusible mass. The production rate, the nuclear reaction rates are going up. The star burns through its mass so much faster. So you've heard me say this 1,000 times before, but really we now have our proof, our evidence, that the more massive the star is, the faster and faster it's going to run out of hydrogen to burn. Well, if it runs out of hydrogen, we know things are going to start getting wonky as it leaves the main sequence. When the hydrogen is sufficiently used up in the core, what's going to happen is that the core will then start to collapse on itself. Fusion processes are going to change, and because of that, there is a decrease in production at this stage. We're going to talk about as we go through stages, does the energy go up or down? And it's a big chain, right? You have to be very specific and say, where in the star's life are we at in that fusion chain? So here's what happens. Run out of hydrogen. When you run out of hydrogen, the star will leave the main sequence, and its core will start to shrink. Now, unlike the low mass stars, helium fusion will pick up a lot faster. All right? We get to that critical electron degeneracy pressure. Remember, we're crushing the core shrinking, and then we reach the critical electron degenerate state. We can't squeeze the electrons together anymore. They're fermions. They're not allowed to be together in that kind of state. So that electron degeneracy pressure triggers helium fusion. You're going to hear me say something very similar near the end of these videos. So keep in mind this idea of crushing something, reaching what's called the degenerate state, and no longer being able to crush any further. So when we reach this stage, helium fusion will begin, and you're going to have a hydrogen burning shell around this. All right? And the stars, if they have more than 10 solar masses, they'll be red supergiants during their helium burning phase. Remember, the low mass stars, say a star like ours, they'll become these red supergiants, and no helium will be burning. They haven't reached that critical degeneracy state yet. So as they do leave that stage, here are these high mass stars, right? They leave that main sequence, and then they start to move basically horizontally across the track, right? Their temperature is starting to go down, but they're also swelling size. The star itself is swelling size, and the combination of the decreased temperature on the surface and the swelling of size causes the luminosity to be relatively flat. But you'll notice there's these bends back and forth. Eventually, a star will reach what's called this instability strip. Right? There's this instability strip. The star is at the stage where it actually begins to pulsate. The star will come in and out, in and out. Its luminosity will go up, go down. Its temperature changes in a very oscillatory fashion. And this is going to be super important for us. Stars crossing this instability state is a very important factor for astronomers. So, we had hydrogen in the core, ran out of it. Now we got helium in the core, burn that up, and eventually run out of that. For the low mass stars, that was the end basically. But the high mass stars, we get to keep going. There's still enough pressure to squeeze stuff together and keep new fusion chains going. So once again, run out of helium in the core temperature and density starts to increase again. There's a little bit of crushing together. And eventually, when that crushing reaches about 8 times 10 to the 8th Kelvin, carbon fusion starts. And the products of carbon fusion, you'll get some oxygen, some neon, some sodium, magnesium. And so we're going up the periodic table as we continue on. And then eventually the carbon runs out, and you're just creating this sequence of different shells of material. At the very end of life, at the very end of this star's life, what you're going to have is a iron core. Iron is the cutoff for fusion. We haven't gotten to that yet, but we will, I promise. You'll have a core full of iron, and each subsequent layer will be a burning shell of material of a slightly lighter element. Start at the heaviest in the metal iron, and then go up. Silicon, sulfur, oxygen, neon, carbon, helium, hydrogen. We keep going out of the core and finding basically like this onion, right? Basically this onion of shells of different materials burning around this. The reason we stop at iron is because fusing iron to heavier elements is what's called an endothermic reaction. In principle, what's happening is that when I smash proton-proton together and eventually get helium, think about all those pictures we had beginning. Photons flew out. Positrons flew out. That was energy. That was temperature to fuel further reactions, right? By smashing things together, more energy came out than was put into smash them together. Iron's the cutoff. Iron becomes an endothermic reaction. For me to get iron to fuse with something and make a heavier element, I need to put more energy in than that reaction pushes out. And that's the end of the chain there.